In section 2.3, we're going to look at characterizations of invertible matrices and bring together a lot of ideas we've covered in the course so far. So section 2.3 is a very quick section and really boils down to this one theorem, the invertible matrix theorem, that says if we have a square n by n matrix, then the following statements are equivalent, which means that they are all true or all false. This is really a recap of everything we've done so far and talking about a lot of ideas that go together. So, when we say that a matrix A is invertible, the definition of that is saying that there is an n by n matrix C such that C times A is the identity matrix, and there's an n by n matrix D such that A times D is the identity matrix. Remember that the difference between these two statements is that there's a difference between multiplying on the left and multiplying on the right when we're talking about matrix multiplication. So we have the invertible matrix A and that definition. We talked in the last section that if we have an invertible matrix, that means that A is row equivalent to IN. Remember that we talked about how to find the inverse is we have AI and we row reduce, and that gets us to I, A inverse. The only way that we are able to do that is to have a row equivalent to IN. And that also means that A has to have n pivot positions, as the identity matrix has n pivot positions, the diagonal positions. Then this also means that the equation AX equals 0 has only the trivial solution. Remember that we always have the trivial solution for AX equals 0, but we have infinitely many solutions if there are free variables. But since we have n pivot positions in an n by n matrix, that means that there are no free variables. It just means there's only the trivial solution. On top of that, that means that the columns of A form a linearly independent set, again, because there are no free variables. Another way to think about that is to say that if we have the equation AX equals B, then that is a consistent system. That's what at least one solution means. A consistent system for each B in Rn. I think the best way to think about this is to imagine that if we didn't have n pivots, then we might have a row of zeros, and this will give solutions for some vectors B, but it will not give a solution if this value is non-zero itself. If we have zeros equal something non-zero. So there's an example of a row of zeros and a vector B such that it's no solutions. But as long as you have the identity matrix as the row-reduced echelon form of our matrix A, then we will always have at least one solution for every vector B. So this would mean no solutions here. Another way to think about this is to say that the columns of A span Rn. We talked about the span of Rn. If we have a span that's not the complete space that we're looking at, for instance, if we're thinking about R3, we might have that the span is just a line or a plane. But if we have three vectors and none of them are multiples of each other or can be written as linear combinations of each other, then we say that it spans the entire set. And that's what it means to be a linearly independent set. Then we have the linear transformation x to ax maps Rn onto Rn. And that's just quick from the columns of A span Rn. When we say onto, another way of thinking onto is meaning that the range is equal to the codomain of the transformation. Note that this is not always true. The range is a subset of the codomain, but if we do have it equal, then it is onto, which means that the columns of A span the complete set, not just a plane or a line or something smaller than the complete set. And then lastly, we have that A transpose is an invertible matrix. We get that straight from a result we talked about the inverse in the last section, that if A is invertible, A transpose is invertible. Now what's important about this theorem is that all these ideas that are not exactly clearly related all tell us the same thing, that this is an invertible matrix, or it's all true if A is invertible. And any of these things can be related to each other. If one of them is true, they're all true. If one of them is false, that's all false. That gives a very powerful theorem here. Let's look at a couple examples of how we could use this theorem. So in example 1, use the invertible matrix theorem to determine if A is invertible, where A is this 3 by 3 matrix. One thing we could do is we could just row reduce this matrix A into row echelon form. We don't even need to bring it into reduced echelon form. If we did, we would bring it down to the identity matrix. But we don't even need to go that far, because once we get into row echelon form, we can see that there are 3 pivot positions in a 3 by 3 matrix. So that means that this matrix A is invertible because there are 3 pivot positions for a 3 by 3 matrix. Now there are many other reasons why we say this is invertible. In fact, anything we did on the previous page, we could say that. We could look at the columns and think about linear independence. We could bring this down to row reduced echelon form like we did and show that it's equal to the identity, as well as a slew of other things. Another example, let's suppose H is a 5 by 5 matrix, and suppose there is a vector V in R5, which is not a linear combination of the columns of H. What can you say about the number of solutions to Hx equals 0? So what we can say is that since V is in R5 is not a linear combination of the columns of H, then the columns of H do not span R5. And this means, by the invertible matrix theorem, that Hx equals 0 does not have only the trivial solution. This means that Hx equals 0 has infinitely many solutions. Remember that this homogeneous system has either the one trivial solution or infinitely many, and the big theorem that we talked about in this section says that if the columns of H do not span R5, that means everything in that theorem is false, including Hx equals 0 has one solution. Therefore, we have infinitely many. To go back to this theorem again, anything that is true in this theorem means that it's all true. And we can relate 2 completely different aspects of this course so far together. And we've hinted at everything in this theorem so far, but now it kind of brings it together fully. This is an important idea to think about. We should be thinking about the way these ideas relate to each other throughout the rest of the course.